corners. Thank you. All right, Jake. Yeah. Logan Williams. Christopher Blake Stafford. Hengfi Liu. L-I-U is the last name. Hengfi. D. L-I last name. Joyce. I started doing it the right way, and I'm Lindsay Hong. This question I forgot to Zancross Group, L-I-U, Zancross Group. Noah Fleece. Finley Mayer. Zachary Smith. Byron Reyes. Scott Lee. Eli Elkins. Z. Lang Zhang. Brian McGarry. Parker Watts. Thomas Chapman. And Hunter Lasby. All right. So, I'm going to tell you, there's going to be a curve on this. It's going to be at least 2 points. I'm not certain exactly what it is yet. I have, I believe, 2 other people that have to take a makeup, and then I'll give you all the statistics, all right? Somebody asked me the average. I'll get you the average. If you want it, I'll get you the average for the exam and stuff like this. I really don't know what it is, but the scores, a bunch of high scores and a bunch of low scores, not a lot in the middle. Some of them, but not like I'm used to seeing. And anyway, I've got my own theories about this, but I wanted to tell you, just encourage you to keep up with this. Don't cram. Please try to do the homework the day or the day after it's assigned before the next class. It will help you immensely to stay on top of it. Cramming for this course will cause confusion, and by the final exam is really when things get bizarre if we don't keep up with it. Now, if you had a problem on the exam, I'm just going to tell you this: shake it off, and remember, this is a small portion of the overall grade. Your final and those quiz grades count for a lot more, and your project. So, I'm trying to encourage you on this one. In all my exams, I can't tell you this enough, are based on the homework. I go through the homework, and what I do is just create problems that use basically the same ideas and concepts applied to slightly different dimensions or frequencies. Something like this. I change it enough so it's not a replica, but if you understand how to do the homework, you usually don't have any trouble with the exams. Do you all realize that all those are homework problems? Every one? All right. So I'm trying to encourage you on this one. And always make sure you know the antenna type. Like short dipole versus half-wave dipole. You've got to be sure to differentiate that and know how to get all the field quantities. Okay. So today, let's see. We talked about what the wire looks like in terms of its internal actually, it's internal inductance and also the wire's resistance, AC versus DC. You had something at the end, that was literally a homework problem, I just put it at the last problem, where you had basically a standard curve and you had to figure out where the actual 3 dB frequency was, which was 1 over 2 pi R times C, and then the resonant frequency was 1 over 2 pi square root of LC, so those things. Then the second part of that was a wire, and I asked for the AC and DC resistance at different frequencies. Now, that was pretty standard stuff. I didn't try to trick you or anything like this, but people did have some confusion. The one thing, so we're done with wires. We did the elements. We did capacitors. We did inductors. We did resistors. We looked at their curves versus frequency. Y'all remember that, everyone? And now what I wanted to do today, I'm going to start this in a second. We talked about grounds. Did we do common mode chokes? Isn't that the last thing we did or not? How many remember common mode here? Anybody? Okay, good. Then in my notes, that's where I'm going to start. And then we'll talk about shields, and then we'll do the digital search. We'll do digital. What's that? We covered shields. Yes, we covered shielding effectiveness and for thin shields, right? Yeah. Okay. And we mentioned filters, but I didn't get into them. Yeah. I asked you, low pass, high pass, band stop, and you had that in some of your other classes, right? We'll talk more about filters in chapter 10. But I want to do the common mode choke next. And in your book, I guess a lot of people won't be here today because there's I guess an industrial, the North Alabama industrial, whatever it is thing, and I hope I sent it to everybody in this class. All right, so now we're going to talk about ferrite chokes. This is on page, it starts on page 537. And these are things that are important to understand. So these are chokes, ferrite, just chokes. Where they're so useful is when common mode currents can be a problem. Now, the most obvious common mode problem happens from lightning striking something and the current coming down to ground. It's common mode because both currents are in the same direction. I'm not sure, didn't I talk about the difference between common and differential modes? I probably didn't. So, and you probably have this in your other classes. Before I talk about chokes, let me just explain something. If you have a current I1 and a current I2, they're running parallel. This would be like a twin lead or something like this. If I1 was equal to I2, it would be called common mode current. It means the currents are the same in the transmission line. Now, if I1 is equal to minus I2, this would be called a differential current. This is the way, that's the current you want. When you have a transmission line, anytime you have coax cable transmission line, and you're sending information between any kind of a source and any kind of a receiver here, you generally have current going that way, same current coming back, and there will be a developed voltage plus or minus. Do y'all follow me in this class? Now that's what you want. What you don't want is lightning that hits this stuff, and this lightning current comes down here and shorts to ground through that. That causes nothing but damage. There are other reasons for common mode currents. One are called ground loops, and I'm not going to delve too far into this, but I want to just let you know. I mentioned ground loops before when we talked about ground loops, just briefly. But anytime you have, let's say I have a pair of wires like this, and this is a source over here, and then I ground this source, and it comes down here, and here's my receiver, and this is grounded. Well, now I have this area here where if there's a time-varying B field in there, it will cause an induced voltage in that loop. Y'all follow me in this class? You know what I'm talking about, right? That induced voltage will cause common mode currents to flow. And those are things that are wicked bad for everything. Over here, you're going to have some electronics that is meant to receive differential information. In other words, plus to minus voltages. When they get common mode currents, they want to find their way to ground, and usually it's by destroying something. Usually, destroying transistors. Usually. Sometimes they can blow a lot of stuff up, but usually it's transistors. Occasionally a capacitor gets blown, but always it's bad. That's what happens. So common mode's very bad. This is what we're working on, chokes to get rid of it. It's called chokes because it chokes out the common mode. That's the reason for that term. So go over here and check around some more things. Still is fun. Right. So when we talk about this is going to be the choke now. So this is the choke. Have you had this in any of your classes? I'm just curious. Common mode chokes. Have you heard the term common mode currents and differential? Is that in your? Help me understand this. This is in your analog systems, your analog circuits course? This is a really important thing. Some of you are going to be doing engineering work, front-end engineering work on equipment where you have to have a real appreciation. So this is the simplest solution, the cheapest, and it works very well. Up to about a gigahertz, somewhere in there. Not super high frequencies, but here's what it is. You have a ferrite core with some mu relative greater than 1. Usually it's higher or something like that. So it does have some loss. And you go ahead and you take this and you're going to wrap it with wire. We make these upstairs. And down here you're going to have it. You're going to wrap it with wire. Like so. You're going to have N turns on both of them. Now, this is a toroid, so think of a donut, all right, or a tube wrapped around itself. It's a circular thing. It has a core area. It's just like this. It's got a cross-sectional area equal to A, which would be pi times the actual radius of the core squared. And that's all it is. They have it. It's about this big. Think of something the size of a quarter. That would be the mean path of those things. And they're about as fat as my pinky in terms of the actual thickness of that. It's very small, but this is amazing how well this works. So, now if you look at that, what does it look like to you, in your own words? Just think of the term. It sure does look like a transformer or a magnetically coupled circuit. Do y'all see that? Now the dot convention is a thing that is important in this. And I'm not going to spend too much time on this, but how many have had Dr. Gross for the dot convention? He is famous for this. The only thing that the dot convention does is tell you if current enters a terminal that's dotted and it causes a flux. In this case, if the wire is wrapped this way, the flux should be going in this direction. You all follow me on that? Magnetic flux. Down here, if you take a look at the same, if you take a current and let it enter the dotted terminal, if it is in the same direction, and it is, then you leave the dots alone. If the current entering that terminal created a flux in the opposite direction, you take the dot and put it over here. You all remember that? I mean, I'm not going to go through much of it. It's that simple. Don't worry about the dot convention. Other than for a common mode choke, you better have both dots on that side of the entry point. So here's what it looks like. Electrically, when they show this, it's this. And here's the dots, so that there's going to be a self-inductance, and it will be the same on both of these. And there's going to be a mutual inductance M. Now, are you familiar with the terms mutual and self-inductance from circuits, right? Is there anybody that's not? Because this is a very common term. Mutual inductance has to do with the coupling between the primary and secondary coil self-inductance has to do with the inductance of the single coil itself. So the equations for this, there's a voltage here that's going to be developed and a voltage here. And if you take a current I1 into here and I2 into here, I'm going to write the equations. Now remember, this is just, I'm isolating only on this choke. There's no other circuitry involved. So if we knew I1 and I2, these voltages that we would get, V1 would be equal to J omega L. We're assuming L's the same in this one. Then it would be times I1 plus J omega M. That's the mutual times I2. How many remember that from your, that's called a magnetically coupled circuit. Y'all remember that? Where'd you get that? Gross's power course or what? How many have had power in here? Okay. So a few of you have. If you haven't had it, it's not hard to follow this. This is basic stuff too. Now V2, here's the difference. And I'm doing this in the frequency domain because it's almost always done in the frequency domain. If it was in the time domain, instead of having J omega, you would simply have L d I dt here. And over here, you would have M, or you had, instead of J omega, you had M di2 dt. That's the only difference. This is going to be J omega, but then it's going to be M times I1 plus J omega, and then it's going to be L times I2. Now the reason they do that is because a lot of times this is written as a matrix. They'll have V here, bar, equal to J omega, and then what they'll call this is L double bar times I bar. It would be, if you think about this, this would be a column vector. The J omega would be out in front, then you would have a 2x2 matrix and a column vector I1, I2. I'm just telling you that's how you'll see it in the field oftentimes. It doesn't have to be just for two. You can extend this down where you can have N leads entering a point. You want to eliminate the common mode on all of them at once, all right? So it doesn't have to be just two, but this is the one that's most common and the one I've made myself. So when I look at this right here, I'll come back over here. Now when you look at V1, when I take a look at V1, if we take a look at common mode currents, it means I1 equals I2 equals IC. You all follow me on this? Now, you come over here, I have V1 is equal to J omega, and it's L I common plus J omega M I common. You all follow me? I'm just writing for V1. Follow me on this? I'm assuming I1 is I2, and that's the case. When I look at this, I have V1 is equal to J omega, quantity L plus M I common. What it means is the impedance of that primary coil really looks like, when I look at V1 over I common, that's the Z common impedance of that primary, I call it for I1, call it primary. And that's equal to J omega L plus M. You all follow this? Now this is important. So in common mode, the impedance for common mode, in other words, the thing that's going to limit this current, is going to be equal to J omega L plus M. You all follow? Now, for the second one, when you take a look at V2 over here, you're going to get the same thing. For V2, you get J omega, and then you're going to get M I common, right? Plus J omega L I common. You all follow? I'm just putting in I1 equal I2, using that formula and putting it here. Everybody follow me? Nothing magical here. This one too has V2 over I common would be a Z. I'll call it Z common 1, Z common 2. They'll be the same. And that's equal to J omega L plus M. So when I look at this circuit right here in the common mode, what actually happens is this. If it is common mode current, I can say what this really looks like. Well, I'll leave it as uncommon. It looks like the impedance here is just equal to J omega L plus M, and the impedance here is simply J omega L plus M. You all follow? Now, that's the impedance picture. If L and M are significant, and that J omega is significant, it will block the common mode currents because the impedance would be very high. That's the idea. Mega ohms is typical. Typically, you're going to get of the order of mega ohms. Y'all follow me? It'll stop it. Now, in the differential mode, and this is where it gets interesting, I'm going to go ahead and put the differential mode up in a second. And let me, first, are there any questions before I move off this? This is pretty straightforward. The only thing you're doing is primary and secondary. Yeah.
We run into cases where the L's are not the same.
No, well, I guess theoretically, somebody could miss a turn or something. The whole purpose of this is to have the same L on both sides. If it's not, then whoever's designing this is really messing up sideways. All right, but you want the L's to be the same. The M is the thing you want to be almost equal to L, and it usually is. This is the nice thing about this. And so in differential mode, which you're about to see, good things happen quick. So now this is all common. When we go to the differential mode, you know what the picture looks like. All right, for the differential mode, that means that I1 is equal to minus I2 is equal to I differential. You all follow? Now, I'm going to just take this equation, and now I'm going to replace I1 and I2 by the differential mode current. So when I take a look at V1, it's equal to J omega, but now it's going to be L I differential right here plus J omega M. Only it's going to have minus I differential, so I'm going to put the minus sign there. I differential. Y'all follow me? Because it turns in the opposite direction. Over here, when I take a look at this, that means when I can factor that out. Now I can factor out J omega, and I can have L minus M, and it's times IV is equal to V1, and V1 divided by IV is now, this is going to be for the differential modes impedance on coil 1, and this is equal to J omega L minus M. Now, you don't want to stop differential mode currents. Ideally, L would be equal to M, so the actual impedance of that would be 0 for the differential mode currents. Do y'all follow? This is the whole reason, and this works. By the same token, if you go down to V2, I'll do it here. When I take a look at V2, I get J omega M, and now that's going to be I differential. You can actually put the minus sign there if you want. Plus J omega, and now it's going to be L I differential here. It won't matter. So when I take a look at V2, I have J omega, and it's going to be L minus M times I differential. And that means the impedance in the differential mode of the second coil, V2 over I differential, here is going to be J omega L minus M. So for the differential mode currents, and I want to make sure I make this point. This is a subtle point, but very important to see. For differential mode currents, we have I differential going there, the opposite current flowing here, and we have some load over here. Now remember, with common mode, both of those currents are going the same way, and they were going to go down here and then to ground. Here, go down, come back here. Y'all follow me? Now the impedance of this coil right here really looks like J omega L minus M, and the impedance of this coil looks like J omega L minus M. Does everybody follow me on this? I'm showing you the equivalent circuit. Well, what that means is when you take a look at the net effect on the impedance of this path, it actually adds twice the impedance of one of these to the path. Do y'all follow me? I want to do an example of this so it's clear. Because this is the one, people only look at one coil, or one, they can easily make this mistake. They look at one side and forget about the other. So in a real problem, let's do a real problem. I'm going to give you some problems with this one. let's say, I don't wanna work from all the numbers, I just wanna show you the example. I have a source here, and we're not even gonna put a source resistance on here. Make it 10 volts peak. And then I have a common mode choke, and I'm looking at the differential mode impedance. So I come over here. In fact, we'll do another problem in a second. And over here, I'm going to have this, and this is J omega L minus M. And now I'm going to have some receiver over here, and it's going to have, I'm just going to say it has an input impedance of R load here. Back here, I have J omega L minus M. And this is my circuit. Actually, why don't I make that voltage just some arbitrary value? You're going to get exact values. Now, I'm not going to actually figure out the value of L minus M and stuff like this for this problem. You're going to do that. But I want to see the effect on V load versus V source. So really, I want to find out what V load is. Well, V load is going to be V source, right? And then it's going to be equal to RL over RL plus J times 2 omega L minus M. Are you with me on this? I'm just trying to be as clear as I can about this. With me? Now, if you want the effects, if you want, say, the load voltage divided by the source voltage, you want this to be greater than like 0.95. You all follow me? You want 95% of the voltage that's going to be at the load to be the source voltage. In other words, this is going to have a minimal effect. Then you can go ahead and, for a given RL and a given frequency, you can solve for what L minus M has to be. You all follow me? It's straightforward there. Then, by the same token, then you can find out the common mode impedance there, and that might have a limit. Maybe they'll say that in common mode we want a single, one of those coils to have impedance of, 1 million ohms or something like this. Then you can figure out what the values for L and M have to be in terms of their magnitude, because the L plus M times J omega will tell you what the common mode impedance is. The L minus M times J omega tell you what the actual value of this is for any percentage. Y'all follow me? And that's important to realize, because you can have L and M as large as you want, as long as the difference between those two remains the same. That's the key. Or a certain maximum or less. But realize this, the larger the value of L and M, the more terms. And if you're making it yourself, I speak from a little experience. Now you can bind these things wound for you, but most of the time, because this is so cheap to do, you're going to get something like that, and you're going to take some shellacked wire, in other words, it's got insulation, and you're just going to thread it and do 50, 60, 70, 80 turns, and do the same on the bottom. That's what I've done before. And that is your common mode choke for most applications that are practical. Now, if you need something with large inductance for whatever reason, maybe you got something, I don't know, for lightning protection, you want a lot of, you want the threshold voltage for arc over to be large, and so you're going to have something more complicated. It's going to be made, it'll be a coil with insulation on it, a lot of turns and stuff like this. Then you'd probably buy it online, but generally speaking, you can make these, they're cheap and they're not hard to do. You with me on this, class? Y'all follow me on this? So make sure you know this. Make sure you know this for Friday's quiz. You hear me? Make sure you know how to do this for Friday's quiz. I'm going to give you some homework on it. So I'm trying to be as clear as I can about this. All right? You'll get homework. It's not hard to understand. And the homework will be it's reflective of the level of difficulty of the quiz. Clear? Look at my old quizzes. You'll probably find a few that are similar to what you're going to see. All right. Next. I've covered shields. I've mentioned grounding. I didn't go through. You have a question? I'm not going to ask you anything about shields on Friday, but I am going to ask you about the common mode choke. away game, right? Or an off week, right? So we're not gonna have all sorts of problems in traffic. All right, so that's the last part of this chapter. And now we get into something that is more complicated. A lot more complicated. And this is true, now in Dr. Whitmer's book, when he talks about differential, or, what is it called? I forget the term he uses here. Digital signals. I've got to tell you one thing. This is the biggest thing with EMC analysis, is understanding how to get the spectrum of digital signals. Bandwidth, in a sense, is meaningless in a lot of ways. So if you have a standard pulse, I'm going to ask you a few things. If you have something like this in the time domain, here we're going to say this is going to be time. This has got a height A and it's got a width tau. That's a standard pulse function. Now, it's either represented as rec t. You could say if this is a voltage V of t, you could say this is A times rec of t over tau. That's one way. The way I'm used to it is saying that A times pulse of tau of t. Either one is just a mathematical representation for that I drew up there. How many have seen one of the two of those? If you had signals and systems, and you should have seen it. Y'all remember this? All right. When you think about this, I'll just do the pulse. If you take pulse transform, this, and you do the Fourier transform of it, what do you get? Well, you're going to get what? Tau, right? And then it's going to be tau, right, times the sinc of omega tau over 2, right? And then A would be in front of it. Y'all remember that? That was a standard waveform. That's in the frequency domain. How many remember that? Right? A pulse goes to a sinc function. You know what a sinc function looks like, right? Sinc function does what? Sinc function in magnitude of a sinc of x looks like this, right? This is down minus 13.2 something 5 dB below this value, and it comes down. Where's the first zero in a sinc function? Where the first time it goes to zero? Remember? Well, what's another way of writing a sinc function mathematically? Sinc of x is equal to what? Sine of x over x, isn't it? How many remember that? I mean, there's a second form of that where it's the sine of pi x over pi x, but they're both reflective of the sinc function. But where's the first zero? How would you find it? If you have sine x over x. Think about the sine function, the one on top. Sine is 0 at x equals 0, right? But the bottom part, the denominator at 0 is 0, so you use L'Hopital's rule. When you do that, you get a cosine of x above, and you get what? 1 downstairs, cosine at 0 is 1. It is 1. All right, in other words, its peak value right here of just the sinc is a value of 1. Where's the first 0? Look at the top. Where does sine go to 0 after 0? Sine of x at x equals 0, sine of pi, right. So this first 0 would be at pi. I'm just trying to make sure you understand. The next peak would be at what? 3 halves pi. It's a peak. The next null would be at 2 pi, right? So you all follow me. That's how you look on top. You don't look on the bottom. The bottom just is taking it down in magnitude, because that's a magnitude. So if you take a look at the spectrum, and this is my point here, for a single digital pulse, the spectrum, what happens is it'll have a value of A tau, but nobody worries about that value. What they worry about are these zeros. And let's just take a look at the magnitude of A tau times the sinc of omega tau over 2. When you look at that value here is going to be A tau. This 0 is going to be when this omega tau over 2 is equal to what? Pi. Y'all follow me? Are you all with me on this one? I'm just trying to show you in the frequency domain what is reflective of what you need to know. Because bandwidth itself really doesn't tell the tale. You don't know what that means exactly. This has got to be equal to pi. Now keep watching just so I can complete this thought. When I look at this, omega is 2 pi f right, times tau, and this is over 2, is equal to pi. I've just gone ahead and just put 2 down here, because that's the argument. A lot of you, if you don't use this every day, you don't remember these transform pairs, but I use them often enough so that I can't get rid of them in my head. Anyway, I look at this, the 2's cancel, right? And what do you see that F is? The first null, right here. F is equal to what? The pi's cancel?
1 over tau.
Right, 1 over tau. Now, that's the null, right? When you think about this pulse is a single pulse. Usually, the pulses that I have here are actually modulated with a high frequency. I'm just trying to tell you for radar applications and stuff like this. So this pulse is just really the on time of a radar signal. I'm going to leave it at that. So really when they talk about bandwidth, what they talk about is the null-to-null bandwidth is really 2 over tau. Do y'all follow? That's one idea of bandwidth. I'm just trying to show you. In Dr. Wentworth's book, I think he calls it this, and he uses a half power bandwidth without saying it. We're going to get to his signal in a second. He says the bandwidth is about 0.5 t rise. He doesn't even talk about this standard thing right here. This is a pulse that has 0 rise time, 0 fall time. Right? Now, but you've got to start here if you really want to understand what's going on when we talk about bandwidth. The next thing I do is now I take a look at a real digital pulse. Has some rise time, has some fall time, has some on time, and it's repetitive. So this is a digital proxy. I want to tell you almost all the problems you run into with FCC compliance issues and everything like that stem from the digital circuitry. Before digital circuitry, back in the 40s and 50s, these problems came always from 60 hertz, but now with digital signal processing and stuff, it's really the digital signal, the clock itself. You've all had to work with JK flip-flops and stuff like this. You did Karnaugh mapping and all that. You had gates and, not, nor, who cares, all the usual dates. I always hated it because if one gate was wrong, everything else messed up, so there's always a problem. But here's the real clock waveform that really is the current waveform you have to worry about. Normally in time, you're going to have something that's got a rise time, then it's got a time that it's on, and it's got a fall time, and then it repeats itself. So we do that, and we just repeat. We're going to assume this is an infinite series for the sake of argument. I'm going to actually do the voltage, but the current will be analogous to this. So this is some V of t, it's a repetitive thing. And when we take a look at this, it has an amplitude of A. It's going to have a rise time tau rise. Dr. Wimmerspoke uses t rise. I'm trying to show it the way, show it a little differently. Here, this is t fall, but we're going to call t fall equal to tau rise. Please make sure you see this. I'll post this information. But are you with me on this one? All right. It's got a certain on time. Now the on time isn't from here to here, it's from the point where it reaches 50% of its maximum value, and that shuts off at 50%. So this is indicated by tau, that's the on time. Then it has a duration, and that duration is called the period t. Sometimes it's called a pulse repetition interval. It doesn't matter the jargon, it's just a period, that's all it is. So when I look at this, one of the important things that you'll see is something called a duty cycle or duty time, and that's simply tau over cap t. You're familiar with that, everybody? Where did you get that? In what course? Digital electronics?
Well, we're working with it in
Embedded systems, but how about a sophomore, junior level course?
Okay.
What course?
Computer systems.
Yeah, is that C. Young Lee's class or?
Used to be no longer.
What's that?
Yeah.
All right, well, you get familiar with this. When you go in the real world, they will talk about this like they use the term resistance, right? You have to be familiar with duty cycle or duty time. It's just the percentage of on time over total time, and it's repetitive. So this pulse goes on forever. Now, the important thing is take a look at the frequency spectrum of this, all right? Everybody with me? And this is where bandwidth and stuff makes a lot more sense. When you take a look at this waveform, I just wanted to show you that open pulse waveform because when you get very fast rise times, fall times, the real thing you worry about is a sync function's representation of that frequency. When you get a repetitive pulse like this, where it has a slower rise time, fall time, then what you have to do is go ahead and say, well, I'll do this for one pulse. I'm going to do this. Some of you are going to wince. Some of you call it a bomb for it. You'll get over it. Trust me. This is one of those things. The math looks really bad, but it gets better. I'm only going to show one period, all right? Now, here, this is the rise time. This is the on time. And we're going to assume this is the rise time too. Usually when you do this, you take the worst of two. Rise time is usually the shortest, just down here. Always find the fastest strand. It's got a height A, and I'm calling this V of t right here. This is just my V of t. So I know from Fourier series analysis, if it is a periodic waveform, you all agree it's periodic, right? It repeats itself forever. I can represent V of t as the summation of C of n e to the j n omega naught t from n equals minus infinity to infinity, where C of n is equal to 1 over t, the integral. Typically I go from minus t over 2 half a period to the middle of the period, from the lower part to the middle of the period there, of V of t times e to the minus j n omega naught t dt. Y'all remember that? That's the exponential Fourier series. By the way, you use this stuff intensely in a lot of courses, in your senior level courses, and all through your graduate level. So you got to get kind of familiar with this. My first experience with this stuff was not in electrical engineering. It was over in the math department. We had all the pure math. We had all sorts of special functions, Bessel functions, Legendre polynomials. We did Fourier analysis. We did it all in the math department. Then you were exposed to it, re-exposed to it in engineering. But here, I think this is, you get it here first, right? Do you get it in the math department or not? I didn't think so, which is a bit, so usually you want to get exposed to topics like this at least once before you enter engineering. You had all the physics, right? In physics, you get all the stuff about resistors and all that stuff, and then you get exposed to it again in your circuits. Usually you get exposed to this long before you get into the double E crystal. So when I take a look at this, you all agree with that, right? Now, if I take a derivative of this, here's where it gets fun. When I take a derivative of V of t with respect to t, take a look. Now what happens? You all see what happens is we take the slope of this line. You all follow me? What's the slope of that line? Because that's what a derivative with respect to time is, right? What is it? It's the height, rise, A, over the run, which is tau rise, correct? So when I look at this derivative of this with respect to t is going to have a value of simply A, and then it's going to be A divided by tau rise. Y'all follow me? Now keep watching. What's the derivative over this range? It's 0, isn't it? It's a flat line. There's no slope. And then here, it's minus, right? Minus A over tau rise. And then it stops right here. And it repeats itself. It'll keep repeating itself forever. That's the derivative. Now come over here and you'll notice something. My V of t here, when I take a derivative with respect to t, what actually happens? Now I get the summation, right? And it would still be from n equals minus infinity to infinity, but would be of j omega times n, j omega n, pardon, times c of n times e to the j n omega naught t. Let me emphasize this point. Take a derivative of this with respect to t, the only thing that happens is you take a derivative of e to the j n omega naught t, which just brings out the j n omega naught. You all follow me in front of that. Everybody with me on this? Now, that's a series that can be represented as simply a summation of some term that I'll call Cn prime, where Cn prime is equal to j n omega naught times c of n times e to the j n omega naught t n equals minus infinity to infinity. Y'all follow me? I simply replaced the Jn omega naught C of n with the term C of n. Y'all with me in class? Why did I do that? Want to take a guess? Because now that is a Fourier series representation. Look up here. Y'all follow me? That means this coefficient can be gotten by saying C of n prime is just equal to 1 over the period of the integral, and you can say v prime of t times e to the j minus j n omega naught t dt. And this is going to go from minus t over 2 to t over 2. Just bear with me. All right. Now you look over here. This is an easier Fourier series coefficient to get than the prior one. Y'all with me? But it's going to get real easy in a second, because I want to take another derivative with respect to time. Everybody follow me on this? I almost think this is blocked. So I'm going to move it over here. All right, now, follow me. When I take another derivative, I'm going to do it over here, because I'm running out of board space. What do I get? I bet you see it. That's right, impulses. And I love impulses because when I do that, they're trivial. That's the reason I'm doing this. So then, when I take a second derivative of v of t with respect to t, and I plot it, now I get this. Take a look. What's the derivative of this? It was 0 and goes to a over tau rise. Isn't that just a delta function times a over tau rise is the weight? Sure. So this is there. This goes there. The height of this is going to be a over tau rise, and it's a delta function. Now, you go on a little bit. This point is actually tau rise here. Now when you hit tau rise, what happens? It was here and it went here. So, same magnitude, only it's negative. Do you all agree with that? And so, at that point, I have this happen. When I'm at tau rise, now I've got this. This is minus a over tau rise, and it's a delta function, and here it would be a t minus tau rise. Do y'all follow? Because the delta function becomes infinite when the argument inside of it goes to 0. So when t minus tau rise goes to 0, it turns on. All other values are 0, and when you look at that, that happens at tau rise. Now I keep going, and over here, this is what? If you look at this, since this is halfway in between, tau, this value right here is at tau as well. I'm going to post some information about this on OneNote so you won't have a problem. Did y'all follow me on that? So when it comes to tau, what happens? When the time, this is time on this axis. Now, it was here, right? It was here, and it went to here, correct? It's negative again. Y'all follow? So now I got another one that comes down here, and this is going to be a value of minus a over tau rise. And if you want the math on this one, it's simply t minus tau, right? Now keep going on. What happens here? This is when I'm at t plus tau rise, right? And it's going to go up to same magnitude, only it's positive. At this point, when I'm at a value of time of t plus tau rise, now I get this. And it's going to be a over tau rise times delta of t minus quantity tau plus tau rise. We good on that one? Mathematically, the only thing we've done is two derivatives with respect to time. That's a series, right? So now we can say that this right here, if I look over here, and I think I'm about out of time, just listen to me now. When I take another derivative of that, what do you see happen with respect to time? Another Jn omega naught comes out in front. You all see that? Everybody follow me on that? Take a derivative of that with respect to time. The only thing that varies with time in there is Jn omega naught. So now I can say that here, the second derivative of v with respect to t squared is equal to that series. I'm just about done. I'm going to have to finish this on Friday, but I want to get you started. Now it's Jn omega naught squared times c of n times e to the Jn omega naught t. This looks like a Fourier series. I can say this looks like c of n double prime times e to the j n omega naught t from n equals minus infinity to infinity, right? Where that c of n prime, the double prime, is simply 1 over t, the integral from minus t over 2 to t over 2 of my v prime, double prime of t, times e to the minus j n omega naught t dt. And the nice thing is, for this one, that c of n double prime is equal to j n omega naught squared times c of n. Now here's the goal on this. I don't have time today. This is integrating a bunch of delta functions. Delta functions are trivial. The only thing you do, find out where they turn on, find out what the value is the function of the functions are adjacent to it at that time. I'm going to finish this on Friday. They're easy. Once I have that, I have c of n. Once I have c of n, or c of n double prime, once I have that, I divide it by j n omega naught squared, and I have c of n. And that is really nice, because I didn't have to do any of the crazy integrations. No integration by parts, nothing. I'll show you the beauty of this. Then we'll get into the spectrum. What you're going to see is some stuff here, not in Dr. Wentworth's book, but this is really interesting. Okay. I'll see you on Friday. Again, common mode choke. I'm going to post all this information. It's laid out perfectly in the information I have.